delta x times beta must equal to omega times this delta t. Or in other words, this peak value, okay, propagates from x equal to 0 to x equal to delta x. This delta x is related to delta t by this term. Of course, this is the distance the wave travels. This is the time, between the two waveforms. Then this must be speed, right? So omega divided by beta is the wave speed. Okay, we call the velocity. So the beta is related to wave speed, velocity. So that's why we call this gamma a propagation constant. Okay? Now, the gamma is a complex number. Real portion determines the loss. Imaginary portion determines the speed. And loss and speed are uniquely defined by RLGC, by the cross-sectional geometry of the transmission line. Okay, that's the frequency domain, the waveform. Okay, and then we can further do some studies, and we found that the coefficients of this right-going voltage wave and to the right-going current wave, this coefficients after a few derivation is equal to the square root of r plus j omega L divided by g plus j omega c. Okay, this is a constant value as long as the cross-section is determined. We define this value characteristic impedance of the transmission line. Okay, so the characteristic impedance of the transmission line is the ratio of the right-going voltage wave to the right-going current wave. Okay, and in general, a characteristic impedance is not an impedance. Okay, an impedance is the ratio of total voltage to total current. Okay, that's something you can measure using your ohms meter. Okay, characteristic impedance is the ratio of the right-going voltage wave to the right-going current wave, not the ratio of total voltage to total current. So this is something you will not be able to measure it using your ohms meter. Okay? You have a 50 ohm cable, and you're trying to measure it, you will never get the 50 ohm in your, not the never. In some special cases, you will get the 50 ohm. But in general, you won't. Yes, sir. Oh, sorry, this is G plus J omega C. Thank you. No, I'm sorry. Didn't pay attention. This is G plus J omega C. G plus J omega C. Is anything more in the previous slides? Here is good. Okay. I'm sorry. This should be C. This should be C. Yeah. That's good. That's very good. Sorry. And similarly, you can find out the ratio of the left-going voltage to the left-going current wave is also Z0, but except there's a negative sign there. The negative sign is because when we define current, we always define the positive current from left to right. Okay. And you talk about the right-going wave, current is going the opposite direction, so you got a negative sign here. But after all, the ratio is, in general, is still characteristic impedance. So the characteristic impedance, again, you see here, only related again to R, L, G, and C. So as soon as your cross-section is determined, the characteristic impedance is also determined. Okay? And this characteristic impedance describes uniquely the ratio of the voltage wave and the current wave that can support in a transmission line. So that's an intrinsic property of the transmission line, very important property. Okay. Okay, so now I can uniquely describe the transmission line using its characteristic impedance of Z0, the propagation constant of gamma. If we try to solve this problem with certain source conditions, certain load conditions, with a length of L, then we can solve this fairly well. But I want to introduce some concept, called refraction coefficient concept. Okay, so the refraction coefficient. Sorry, this has something to do with the PowerPoint. Okay, this is equal sign, definition sign, but somehow becomes to a block. So that's definition. The gamma is defined as the ratio of the refracted wave to the incident wave. And in our case, our source is at the left side. So the refracted wave is the left going wave. The incident wave is the right going wave. So when you apply a source, you launch a wave from left to right. And the reason you also have left going wave is at the load that the wave will get refracted. So you got the left going wave too. So the ratio of left going wave to right going wave is called the reflection coefficient. And we find out that at the load, this refraction coefficient is related to the ratio of, is the difference of the load impedance and the characteristic impedance. Okay, so this simple expression can be used to calculate the refraction coefficient. And when you define the refraction coefficient at x equal to L, at any arbitrary x, you can find, this refraction coefficient, the ratio of the refraction coefficient. After you get the ratio of the refraction coefficient, we can further solve the input impedance. The input impedance is defined at, at this source location. You're looking into the transmission line. What is the total equivalent impedance? The ratio of the total voltage to the total current. Okay, you find out that this input impedance is related to the characteristic impedance, is a function of the load, is a function of the gamma and the length, determined by the length. Different the length, you would see different kind of impedance. Okay, I didn't have more thing here, but let me quickly talk about a few special transmission lines. Okay, so if this ZL is equal to Z0, then you will find out the refraction coefficient is 0. So in other words, the left going wave is 0. You only have right going wave. So the source will launch a wave, the wave hits this ZL. It will never get refracted. It's actually completely absorbed by the load. So we call that line a matched line. Okay? In a matched line, if you go through this input impedance expression, you find out the input impedance is always equal to Z0, always equal to the characteristic impedance of the transmission line. So you actually can measure the characteristic impedance of a cable if you match it at the other end using an ohms meter. Then you can measure 50 ohm. That's the only case you can do that. Okay, that's a special case. And what if this load is a short? If it's a short, you notice this gamma L becomes -1. Okay, in other words, the left going wave and the right going wave are in the same magnitude. We call that a complete reflection. All the wave propagates, hits the load, will completely refracted. And that's really bad for signal propagation because no power is delivered to the load. Everything is bounced back. Okay. Another case is this load is infinity. Then the gamma L is equal to +1. Okay, again, that's another full refraction. Nothing goes to the load. Okay, the wave is completely bounced back. In any general cases, it's between the gamma L is between 0 and 1, the magnitude. Okay, and the input impedance becomes a complex number. All right, so when we have this transmission line concept, then we can further derive a little bit to understand the scattering parameters. It's very useful at the high frequencies to describe the behaviors of a geometry. So if we have something, a black box. We don't know what's inside of the black box, okay? We're trying to describe the behavior of this black box. One way to do it is to relate the terminal behaviors, together to describe the behavior of this network. That's called the network analysis, okay? So at the higher frequencies, we can assume that a network, an unknown network, is connected to two transmission lines. And these transmission lines has the characteristic impedance of Z01 and Z02. Then in this transmission line, we have left-going waves, right-going waves here. Because we have multiple ports, we don't know which is left and right in general cases. So we rather call them incident wave, the wave into the port, and the wave come back, refracted waves, okay? So in each of these transmission lines, there's incident wave, refracted waves. Then I can relate all the refracted waves with the incident waves using a matrix. This matrix is called the scattering matrix, okay, S parameters. And if you look at this S11 definition, this S11 is actually the ratio of the refracted wave in this port 1 to the incident wave at the port 1. So this describes the refraction of this network occurs at this junction, okay? So this S11 actually is a refraction coefficient, okay? Now, if you look at the S12, S12 is related to B1 to A2, okay? So this actually is a transfer function, describe how much wave, propagates from port 2 into port 1 through this network, okay? So the S parameters at the end of the day are just the refraction coefficients and transmission coefficients of this unknown network. Okay, so why it is popular? Because at the high frequencies, it's easy to measure the waves than the voltages and the currents. Believe it or not, at the high frequencies, the measurement, the accuracy of voltage and the current measurements are pretty poor. Okay, so we cannot do it easily at these locations to measure voltage and the currents. So it's very popular that we do the S parameters, and the measurement is done by the vector network analyzer. So network analyzer is a key instrument for high-speed circuits. Okay, after I finish the frequency domain, let me quickly talk about the time domain solutions of the transmission line. I only use lossless transmission line for simple mathematics here, okay? So let's assume R and G equal to 0. I can give you some expressions. Now this time, the general solutions, voltage and the currents, are still a sum of the right-going waves and the left-going waves. So at the NL location, if you need to find a voltage at the NL location X, you need to find the right-going wave and the left-going wave and then add them together to get the solution, okay? And the voltage and the current is still related by the characteristic impedance Z0 here. So pretty much the same as we described in the frequency domain. We draw this again in the time domain that at a particular time T1, when you have a waveform in the transmission line, at the T2, then the waveform actually shifts a little bit described by this particular function. So the relationship of T and X in this function describes whether it's right-going wave or left-going wave, okay? And then now, the difference, these are all look similar. But the difference between time domain and the frequency domain is in the time domain, we care about the transient response, okay? That's what we care about in digital circuits too. We want to see when the signal transients from logic 0 to logic 1, what happens immediately. We don't care about, in a day, what's the response there. We care about immediately after the transition, what happens. So the transient response we have to look at a time, it's a function of time, and this function of time introduces a concept of the wavefront. So it always takes time for the wave to propagate from one location to another location. And if you don't give enough time, it will not reach completely from the start point to the end point. There's always one location that's the front end of the wave. Before the front end of the wave, nothing happens because the wave hasn't reached there yet. So the voltage and the currents are zero. Only behind of the wave front, there's voltage and the currents. That's the difference between frequency domain and the time domain. So in the time domain, we start with an initial wave. We see at the t equal to 0, we put in a voltage here. We want to know what is the initial wave that the wave goes out. Okay? This wave can be calculated because we're in the time domain. When the wave is generated at x equal to 0, what the wave sees is only the characteristic impedance of the transmission line. It only sees this waveguiding structure. It doesn't know at the end of the line what's the load condition is because the wave hasn't reached there yet. Okay? So at that particular time, what the wave sees is the characteristic impedance. So we can easily find out this voltage at this input side is a voltage divided through these two different resistors. Okay? And this total voltage is equal to the initial right voltage going wave because we only have one wave at that time. Left going wave hasn't been generated at all at that time. Okay? So from this expression, we can easily find out the initial right going waves. Okay? Then over time, the wave will propagate down to the transmission line at a certain time, at t equal to td, the delay of the transmission line. The wave now reaches at the load. As soon as it reaches the load, depending on this resistance, it will get refracted. The refracted left-going wave can be calculated using this refraction coefficient. So if we take a refraction coefficient times the input wave, we get the refracted wave. So you start at t equal to td, you start to have a left-going wave. And this left-going wave starts at the load point, and it takes time for it to propagate back. Only at t equal to 2 times of the td, this wave reaches at the front, then maybe get refracted by this RS again, generate another right-going wave. Okay? And that re-refracted wave will propagate down, generate another left-going wave. So the wave just going bounce back and forth over time. Of course, if you wait long enough, okay, you add all the right-going waves together, that becomes the right-going wave in the frequency domain because the frequency domain is a steady state solution. So anyway. Okay, so to better help us to track, where the wave is at a particular time, where is the wavefront, we use so-called bounce diagram that helps us to, track each waves, going down and, back and forth in the transmission line. So each of these waves describes, each location. You notice the horizontal axis is location, vertical axis is time. So at each location, each time, this describes the front, wave front of that particular wave. So this is the initial wave. At the 3.8 nanosecond, it got refracted. Some other wave got transmitted. And the transmitted wave will get refracted coming back and go to transmitted, refracted again. At here, it stops here because this impedance is the same. It's matched with this transmission line, so it's completely absorbed. So this diagram helps to understand how the wave propagates in the transmission line. It's a very useful wave to help us to understand. Okay, I will skip out some of the slides here, but basically using bounce diagram, we can calculate the total voltage at a particular location over time, okay? Or we can calculate voltage or current distribution at a particular time instant along the entire transmission line. That's all possibly done. Okay, now the next interesting topic is I want to show the so-called TDR measurement, okay? And it's a very useful measurement in the time domain for transmission line kind of structures. A so-called TDR measurement, the TDR source, is actually very simple. It includes a step source together with an impedance, okay? And this source, will generate a wave into a transmission line, and at the same time, this instrument will measure the total voltage right at the output side. Remember, it measures the total voltage, okay? So for this simple case, if we do this, bounce diagram, we know initially we have a right-going wave. At the TD, we generate a left-going wave. And this left-going wave, when it reaches to the front, generates another right-going wave, and go on. That's the total. That's the bounce diagram. If we draw the total voltage at this input side, this total voltage starts with a constant value of some voltage, and at some time it jumps to another voltage. Okay, this is what we can measure, at the front end of the transmission line using the TDR. And this two voltage and the time information gives us critical information about the transmission line. Okay, first of all, this initial voltage, okay, between t and this time, this is the initial right-going wave. This initial right-going wave, as we said, is a ratio of 50 ohm and Z0. So from the voltage 1, we can get the characteristic impedance of the transmission line, okay? And this time, T0, the time that the voltage starts to jump, must be the refracted waves reached at the front end. Notice we are observed at the front end here, okay? We won't see the left-going wave until that left-going wave reaches back. So this time from start point to that time is 2 times of the delay. So if we found out the time, at this junction the voltage changes, then immediately we know the delay of the transmission line is a half of this time. So we actually know, okay? And then this voltage is actually the sum of all these 3 waves added together. And then from this voltage level, we can calculate the load condition, okay? So a TDR measurement is very useful for transmission line measurement. We can easily measure its characteristic impedance. And more importantly, the time axis is related to the length of the transmission line, okay? So if there's anything wrong in your transmission line, okay, you can see it in the time domain behavior, and that the particular time corresponds to the location of the event. So it is a very useful tool, help us to debug what's going on in the transmission line. Yes, sir.
When you know how you said in the bounce diagram,
yeah,
it reflects back.
Yeah.
Because of discontinuities
because of the load. This load is not matched with this impedance, then it will bounce back. Yes. If they are matched, you won't see that refracted.
Whenever it continues on,
Then you don't.
so when you have the bounce back, that's the reflection loss, and then whatever continues on is your insertion loss, or is that how it goes? Or
The insertion loss and the refraction loss is a good question. It's actually in the frequency domain concept. It's actually in here when we talked about the S parameters. Okay, so when you have some device you put into your measurements, if you see a refraction at one of the ports, the refraction, we usually, if we take the log definition, we call the return loss. Okay, so the 20 log 10 of this S11 is the return loss. And the S21 or S12 is called the insertion loss that describes, the loss from one port to another port, okay? All right, so TDR is a really important measurement. Not only it measures the characteristic impedance and the resistive terminations later on. Here, let's do a little bit simple cases in the previous diagram. So here, it's at t equal to 0, it all jumps to certain voltage. Okay, we notice if the voltage is half of the source voltage, then immediately we know the characteristic impedance is the same as the instrument impedance, 50 ohm. Only when two impedances are 50 ohm, then you got a half of the source voltage, okay? So that means all these Z0s are 50 ohms, okay? Now in this case, if this at a certain time, it from half of the source voltage jumps back to 0, that tells us your load is a short, because the short has a -1 refraction coefficient, okay? When it comes back, when you add them together, you get them canceled, it becomes 0. So if we see at this junction, the total voltage comes back to 0, then we know, oh, this is a transmission line terminated with a short circuit, okay? If actually goes up to be the voltage, total voltage, then it must be an open, because for open, the refraction coefficient is +1. So you add your initial wave plus the refracted wave, you got 2 times of that at that critical point. If you see this voltage never changes, then you have a matched load. There's no wave refracted back. So a matched transmission line equivalently like an infinitely long transmission line. The wave propagates down, never comes back, okay? And in general, if you have some resistive load, if this load is greater than 50 ohm, then at this location you would see a voltage greater than the initial voltage. If the voltage here is smaller than the initial voltage, this load must be smaller than characteristic impedance. So from the TDR measurement, if you know the topology of your device, you can easily come up with this understanding. Okay. And in the time domain, we can also deal, in addition to the resistive components, we can also deal with C and L components, okay? But the C and L components are difficult because we cannot use impedance or, concept. In the time domain, we don't have J omega, okay? So we really have to solve partial differential equations. But there's an easy way to understand these capacitance and inductance behaviors. The capacitance is a voltage storage device. If you think about it, when the wave hit this capacitor, initially, it looks like a short circuit, okay? Because of that circuit behavior, it looks like a short circuit. But over time, if you wait a long time, this becomes an open, okay? So it starts like a short and eventually becomes an open. So you can think about when wave hit this junction, immediately it sees a short circuit, but gradually it becomes an open circuit. So you see this wave is interesting. It starts at half of the voltage, and immediately when it sees this junction, it likes a short. A short, as we said earlier, it will go down. The voltage will try to go down to 0. But over time, it becomes an open. When it becomes like an open, the total impedance, because this is an open, so the total impedance is dominated by Z0. So it backs to 0. So if you see something in your TDR that go a dip, and the back there must be a capacitance somehow, a shunt capacitance in your loop, in your circuit. And the inductance is slightly different. It's opposite. Initially, when you hit this inductance wave, the inductance behaves like an open circuit. But over time, it becomes like a short circuit. So if you see here, when the wave hits this junction, it sees an open initially. So it tries to go up. But eventually, over time, it becomes a short. So it becomes Z0. So a little bit, peak means that's an inductance. Okay. So if you see something goes a peak and then a dip, that's an inductance with a capacitance. Or you start with a dip and then a peak here. That starts with a capacitance and inductance. So you actually, from TDR, you can come up with certain, topologies. You can see what happens. So what relates to this capacitance? What relates to this inductance? We use this a lot for layout checking. So especially when, for example, you start with a via structure, then go to a trace. Okay? So you want to see what happens. Usually, you would see a dip first. That's because the vias are capacitive most of the time. So it's a capacitive. And then you may have, a tip here, because when the via to the trace connection, the trace portion, because of the antipad, the trace portion, that doesn't have the return path, it's more like a little bit inductance. Okay. So often you would see some kind of this case when you have a via to trace connection. So if this dip and the peak are getting too large, you need to tune your design. If that's too much capacitance, what can you do with your via design? Maybe your antipad needs to be a little bit far away so that the capacitance becomes smaller. Okay. If you have, too much an inductance, maybe you need to provide a certain return path in the junction, then so that the inductance becomes smaller. So the TDR is very useful in design.